Hello friends. In last lecture we learned about double sideband suppressed carrier modulation and how to improve power efficiency of the modulated signal. In this lecture we are going to learn single sideband suppressed carrier modulation and how we can further improve the power efficiency of modulated signal. The left hand side figure shows time domain and frequency domain of double sideband suppressed carrier modulation, and the right hand side figure shows time domain and frequency domain of single sideband suppressed carrier modulation. In the left hand side figure, you in figure C, you will find there are two sideband. One is upper sideband and another one is lower sideband. So we are transmitting the information with the help of two sideband, upper sideband and lower sideband, and both the sideband are identical. And so so we can transmit our information with single sideband as both are identical, so we don't need both sideband. We can convey the information by a single sideband. So we will suppress one sideband to make it further power efficient. So in the right hand side figure you will find that we suppress the upper sideband and we are only transmitting the lower sideband. Single sideband suppress carrier modulation. In last slide we had seen about frequency domain of message signal. In this slide, we will see frequency domain of single tone baseband signal, single tone message signal. By single tone, we mean only one frequency is present in message signal. That is given by mathematical formula xt is equal to x cos omega mt. So frequency domain of xt is given by first figure, upper one figure, where we have two impulse at minus omega m and at plus omega m. And when we do it, when we perform double sideband suppressed carrier modulation on this, then we will get the frequency spectrum as shown in middle figure xt cos omega ct, that is double sideband suppressed carrier modulation. We will get two impulses around carrier frequency. One is at omega c minus omega m and another one is at omega c plus omega m. So so we if we suppress the upper sideband, then we will get only one impulse, only one lower sideband impulse, that is at omega c minus omega m at positive side, and at negative side we will get minus omega c plus omega m impulse at minus omega c plus omega m. So from the frequency domain, we can conclude the mathematical formula of single sideband suppressed carrier modulated signal here. So we can define st is equal to 1 half x cos omega c minus omega m multiplied by t. That is for lower sideband signal, lower sideband modulated signal. For upper sideband modulated signal, we will get st is equal to 1 by 2 x cos omega c plus omega m multiplied by t. So we got the time domain formula of single sideband suppressed carrier modulation. Now let's further explore the mathematical formula of single sideband suppressed carrier modulation. St is equal to 1 by 2 x cos omega c minus omega t minus omega m multiplied by t, that is for lower sideband. And when we will simplify it, we will get st is equal to 1 by 2 x cos omega ct multiplied by cos omega mt plus 1 by 2 x sin omega ct multiplied with sin omega mt. And here x sin omega mt is 90-degree phase shifted version of baseband signal x cos omega mt. So if we write x sin omega mt as x ht, here h is Hilbert transform, Hilbert is a filter that is used to get 90-degree phase shift of any signal. So we can rewrite our single sideband suppressed carrier modulated signal as 2st is equal to xt cos omega ct plus xst sin omega ct. That is for lower sideband suppressed carrier modulated signal. For upper sideband suppressed carrier modulated signal, we will get 2st is equal to xt cos omega ct minus xst sin omega ct. Now, how to generate single sideband suppressed carrier modulation? There are two methods to generate single sideband suppressed carrier modulation. One is filter method, and second one is phase shift method. Filter method. In this method, we we simply we simply apply a band pass filter on the double sideband suppressed carrier wave, double sideband suppressed carrier modulated wave, and we get single sideband suppressed carrier modulated wave at output. You can see the block diagram here. Message signal and carrier signal are applied on product modulator, which gives double sideband suppressed carrier modulated wave, and when we pass this through band pass filter, we get single sideband suppressed carrier modulated wave. So regarding filter, we know filter has there is limitation of filter that there is in practical there is no filter which cut off frequency very sharply. There is gradual cutoff of frequency at either side of band pass filter. So if upper sideband and lower sideband are connected at omega c carrier frequency, then filtering will give some portion of another sideband. So we perform single sideband suppressed carrier modulation on only those signal which have some distance from carrier frequency, which are not present at carrier frequency after modulation. This is the limitation of single sideband suppressed carrier modulation method. The second method is phase shift method. Earlier we had seen mathematical formula 2st is equal to xt cos omega ct plus xst sin omega ct for lower sideband, where xst is 90-degree phase shift version of message signal. So block diagram of phase shift method single sideband suppressed carrier modulation scheme is shown here. Here the message signal and the carrier signal are applied to modulator 1 and modulator 2. At modulator 1, we directly apply message signal and carrier signal. But at modulator 2, we apply 90-degree phase shift message signal and 90-degree phase shift carrier signal. And we perform summation of these two to get lower sideband suppressed carrier, lower sideband suppressed carrier modulation. Now, demodulation of single sideband suppressed carrier modulation. This is done by same as double sideband suppressed carrier demodulation by using synchronous detection method. In synchronous detection method, we multiply the received modulated signal with carrier frequency. So the mathematical formula of multiplication is 2 st multiplied by cos omega ct is equal to xt cos omega ct plus xht sin omega ct multiplied by cos omega ct. On simplification, we will get 2st cos omega ct is equal to 1 half xt plus 1 half xt cos 2 omega ct plus xht multiplied by sin 2 omega ct. So we can see here the message signal is one half of xt, and rest is unwanted unwanted part. So we want to filter out the second term, and we can do so by passing it through low pass filter, as low pass filter will not pass to uh, 2 omega ct frequency. It will only pass one half of xt. So you can see the block diagram of single sideband suppressed carrier demodulation. Now, vestigial sideband modulation. This one is same as single sideband suppressed carrier modulation. You can see the the block diagram of vestigial sideband modulator. It is same as single sideband suppressed carrier modulation scheme, and the only difference is here we know no, the filter is practical one, and it will not cut off the other sideband other sideband component completely, because filter response is gradual. So we can see the spectrum of vestigial sideband modulation. The upper figure is spectrum of baseband signal, and the lower figure is spectrum of vestigial sideband modulation. Uh, here we are here we are using band pass filter, but this band pass filter is uh, passing almost full amount of lower sideband, but with some amount of upper sideband, some portion of upper sideband, and we can perform vestigial sideband modulation even in that case uh, where the baseband signal is present at around carrier frequency, also is present at the we use this even in that case where the message signal has DC component also, or in module double sideband suppressed carrier modulated spectrum, fre- frequency component presented FC at FC also. And for demodulation of vestigial sideband modulation, we do the same method as we do in double sideband suppressed carrier modulation, that is synchronous detection method. With the help of synchronous detection method, we get the message signal from vestigial sideband suppressed carrier modulation. With this, we completed all the aspect of amplitude modulation. Thank you.